Section 3.6, this is the last section in Module 3. We're going to be working with rational functions and inequalities. Rational functions we're still working with the polynomials that we've been discussing, but rational function just simply means that we're going to divide one polynomial by another. If you notice it's based on the word ratio, so you're looking at fractions. So we've got fractions where we've got one polynomial in the numerator and another polynomial in our denominator. Examples of rational functions. Well, before I continue, you should obviously have your notes printed out in front of you. And you may have noticed the last two examples, example 4 and example 5, they have class example written beside them. We're not going to do those two examples in the video. We're going to talk about those together in class after you've had an opportunity to think about some of this. I don't want to throw it all at you at once. I'd like to give you an opportunity to practice it, and then we'll continue our discussion in class. When I'm checking for your notes, I will not expect to see anything filled out for example 4 or example 5. I'll only be looking at examples 1 through 3. So what do rational functions look like? Well, they can look like this: f of x equal 1 over x. That's the most simple rational function that we can possibly work with. It's just got a single x in the denominator. Other examples might be x plus 1 over 2x squared plus 5x minus 3, or 3x squared minus 3x minus 6 all over x squared plus 8x plus 16. So again, any function where you have a polynomial divided by another polynomial. That's what we're working with here. What do these graphs look like? Let's just talk for a moment about this most simple function, f of x equal 1 over x. If we think about the domain for this, with this having an x in the denominator, there is one possible value that you might try to put into this function that will not give you a value back. If x is in the denominator, then you know that you cannot divide by 0. So the domain for this first example would be, I'm just going to squeeze it in right here, my domain would be all real numbers except 0. So I can say all real numbers except x cannot equal 0. That is indicated in the graph of this function. Notice there is no x value equal to 0 ever. If you go to 0 on the x-axis at the origin, there's no function value there. The domain restriction creates what we call a vertical asymptote in our graph. Since x can never equal 0, the line x equals 0 is a vertical asymptote, meaning that our graph can never touch that vertical line x equals 0, which of course is the same thing as the y-axis. So that's why we've got this funny looking shape to our graph, because our function value can never equal 0. So this graph can never take on a y value of 0, ever. It also happens to have a horizontal asymptote at the x-axis, and that means that our graph can never touch or cross the x-axis. So an asymptote simply means that you have a line. It might be a vertical line, it might be a horizontal line, but you've got this boundary that your graph can never touch or cross. That's what an asymptote is going to do. So looking at the bottom of the page, we've got a vertical asymptote. That's a vertical line that the function approaches but does not touch. Horizontal asymptote is a horizontal line that the function approaches but does not touch for at least one portion of the function. What this is saying is that it is possible that the graph might actually touch the horizontal asymptote. However, the horizontal asymptote still serves as a boundary for part of your graph that it cannot touch or cross. The oblique asymptote, this is a non-vertical, non-horizontal line. What does that mean? It means it's a slant line like this, that the function approaches but does not touch for at least one portion of the function. Okay, so if you recall, with a slant line like this, if you go all the way back to Algebra 1 and remember y equal mx plus b, where m is your slope, b is your y-intercept, we will be using this to help us graph our oblique asymptotes. So just just keep this in mind, that you're going to be using the y equal mx plus b to help you graph your oblique asymptotes. Okay, so let's look at page 2. How do we determine asymptotes? A very important piece of graphing rational functions is being able to determine your asymptotes, because your graph is going to have to work around those asymptotes. To find the asymptotes of a rational function defined by a rational expression in lowest terms, it's important that we're in lowest terms. If we're not in lowest terms, then we're going to have to put it in lowest terms. Use the following procedures. For a vertical asymptote, we find any vertical asymptotes by setting the denominator equal to 0 and solving for x. This is just like finding the domain. It's the same thing here. If a is a 0 of the denominator, then the line x equal a is a vertical asymptote. What is that saying? So let's say you've got f of x equals 4 divided by x plus 1. What is a 0 of that denominator? What is a 0 of that denominator? Well, it would be the value for x that will make that denominator equal to 0. And that would be -1. If you put -1 for x, you get 0 in your denominator. So just like we saw with domain, if we do our domain, we would have all real numbers except x cannot equal -1. The vertical asymptote would be the line x equals -1. So we say our vertical asymptote for this example would be x equal -1. Just for this example here. This is something I just made up off the top of my head. But that's how you'll find a vertical asymptote. How do we determine our non-vertical asymptotes? Meaning whether we've got either a horizontal asymptote or an oblique asymptote. Remember, oblique means it's a slant line. Oblique is going to look like this, like this, or maybe like this. That's what oblique asymptotes look like. If the numerator has lesser degree than the denominator, then y equals 0, or the x-axis is a horizontal asymptote. What does that mean? Well, let's just look real quickly back at the very first page and talk about degree. Now, we've talked about degree before, but just as a review, degree is going to be the largest exponent that you see in your polynomial. So in my first one, 1 over x, my numerator has degree 0 because I don't have an x. It's just x to the 0 power. My denominator has degree 1 because I've got x to the first. In my second example, my numerator has degree 1 because the exponent is x to the first. And my denominator has degree 2 because the largest exponent is the square. So that's what we mean by degree. So it's saying that if the numerator has a smaller degree than the denominator, then y equals 0, or the x-axis is a horizontal asymptote. Part B. If the numerator and denominator have the same degree, for example, you might have y equals 2x cubed minus 4x divided by 5x cubed plus 7x squared minus 8. Okay, the numerator has degree 3 and the denominator has degree 3. So if the numerator and denominator have the same degree and the function is in this form, now what this is just simply saying that the largest exponent is first. That's all this stuff says. If the largest exponent is or the leading term is in the very front, then the line y equal a sub n over b sub n is a horizontal asymptote. A sub n would be the coefficient on the leading term, or the term that has the largest degree. So in this example, my leading term is the 2x cubed in the denominator and the 5x cubed in the 2x cubed in the numerator and the 5x cubed in the denominator. So to determine my horizontal asymptote here, I'm only interested in these first two terms. Just looking at this part. What is the line y equal a sub n over b sub n? In our case, it's going to be y equals 2 over 5. That would be my horizontal asymptote. And that's it. That's all I have to do to get my horizontal asymptote. So horizontal asymptotes are really easy. You just have to keep in mind if your numerator has a smaller degree than your denominator, it's just going to be y equals 0. If your numerator and denominator have the same degree, then it's just going to be the leading coefficient in the top divided by the leading coefficient in the denominator. Part C. If the numerator is of degree exactly one more than the denominator, there will be an oblique or slanted asymptote. To find it, divide the numerator by the denominator and disregard the remainder. Set the rest of the quotient equal to y to obtain the equation of the asymptote. What is this saying? Long story short, if you've got y equals, and let's say you've got 4x squared minus 5x plus 3 divided by x plus 5. The numerator has degree 2, the denominator has degree 1. So the numerator is exactly one more than the denominator. Then that means that you can divide, since the degree of the numerator is larger than the denominator, we can divide the top by the bottom. How can we do that? We can, well, for the problems that we're going to be working with, we can do synthetic division. I think I'm sorry, I take that back. I think there might be one in the homework that comes up where you cannot use synthetic division. When do we get to use synthetic division when we're dividing polynomials? Do you know? We can use synthetic division if we are dividing by x to the first. If you're dividing by x squared or higher, you will have to go to your long division method. And that will happen in the homework. I think you're going to have to divide by maybe x squared. So, but if you're just dividing by x to the first, then go to the synthetic division. And that's what we'll do here. So if the numerator is of degree exactly one more than the denominator, there will be an oblique or slanted asymptote. To find it, divide the numerator by the denominator, disregard the remainder, and then set the quotient equal to y to get the equation of the asymptote. I'm not going to do this example, but we're going to do another one in a second, doing the same process. We do have a note about asymptotes. This is very helpful here. The graph of a rational function may have more than one vertical asymptote, or it may have none at all. The graph can never intersect a vertical asymptote. Okay. However, there can be at most one other non-vertical, meaning horizontal or oblique asymptote, and the graph may intersect that asymptote. Okay. You can also add to this. If you have a horizontal asymptote, you will not have an oblique asymptote. If you have an oblique asymptote, you will not have a horizontal asymptote. So you might want to write that down. If we have a horizontal asymptote, we will not have an oblique asymptote, and vice versa. If we have an oblique asymptote, we will not have a horizontal asymptote. So this will save you a lot of time looking for asymptotes that may or may not exist. Okay, so that's what I wrote on there. And we are ready to go on to, I believe, our first example. First example, we're just practicing finding asymptotes. Example 1, find all asymptotes. We got a part A and a part B. Okay, so we're going to do vertical asymptotes first. Vertical asymptotes are just like finding the domain. You set your denominator equal to 0, and you solve it. It's also like finding X-Intercepts. So what do you do? Well, I'm sorry, it's similar to finding X-Intercepts. I shouldn't say exactly the same. How do we solve this? We've got a quadratic equation. Let's see if we can factor it. I can do 2 times 3. I'm going to make my 3 negative and my 2 positive. I get x plus 2 equals 0, or x minus 3 equals 0. So I get x equal negative 2, x equal positive 3. So I have 2 vertical asymptotes. The non-vertical, the horizontal or the oblique. First, let's determine which we have. So you go back to the previous page and look at parts A, B, and C, where we're to help us determine what kind of asymptote we have. If you have an oblique asymptote, that means that you can divide your denominator into your numerator because you're going to do synthetic division. Can I divide this denominator into this numerator? No, because x squared is bigger than x, so I cannot divide, so that means I do not have an oblique asymptote. So I can say no oblique asymptote. But if I don't have an oblique asymptote, then I better check for a horizontal asymptote. What are the rules about horizontal asymptotes? Either it might be y equals 0. It's y equals 0 if the degree of the numerator is smaller than the degree of the denominator. If the degree of the numerator and denominator are the same, then it's going to be y equal a sub n over b sub n, the coefficients. Which case do I have here? Well, my numerator has degree smaller than my denominator, so I have a horizontal asymptote of y equals 0. Okay, I was not asked to graph this, but I'm going to draw it just so you can see what this means. I'm not going to graph the whole thing, but I'm going to show you how we can use this to help us figure out what's going on with our graph. We've got a vertical asymptote at x equal -1. So here's -1. I'll draw a vertical dotted line through this. So that's the boundary that my graph cannot touch or cross. I have another vertical asymptote at x equal 3. So this divides the graph up for me into 3 sections. I've got something going on back here. I've got something different going on in between the 2 asymptotes, and then I've got something else going on out here on the right. The horizontal asymptote is at the line y equals 0, which is the same as the x-axis. So this gives me another boundary where it's going to divide my graph into a top and a bottom piece. So it might be doing one thing here, and I don't know exactly what it's doing, but it might be doing something here like this, maybe doing something down here like this, and maybe something up here like that, something along those lines. So those asymptotes are very helpful to get a picture of at least to start to get a picture of what's happening with our graph. Let's look at part B. Here we have f of x equal x squared plus 1 over x minus 2. Let's determine our vertical asymptote first. For the vertical asymptote, we set our denominator equal to 0. Solve for x. We get x equals 2. So we have a vertical asymptote at the line x equal 2. What about the non-vertical? Do we have oblique or do we have horizontal? Well, I'm going to put oblique asymptote and I'm going to put horizontal asymptote, and we'll decide which one we have. This time the numerator has degree 1 more than the denominator. The numerator has degree 2, the denominator has degree 1. I can divide my numerator by my denominator using synthetic division. So this one has an oblique asymptote. If it has an oblique asymptote, what does that tell me about my horizontal asymptote? For the horizontal, I can say none. So how do we find our oblique asymptote? We're going to set up a synthetic division problem. Again, because how do I know that I can use synthetic division? Because my denominator has degree 1, it's x to the first power. So I get to set it up using synthetic division. I'm going to change the sign of the -2. I'm going to put a +2 here. And then inside I need to have a 1x squared. Notice that there's no x term, so I need a 0 for a placeholder. And I've got a constant of 1. Bring down my 1. 2 times 1 gives me 2. Add. 2 times 2 is 4. And I get 5. My remainder is 5. What did the rule tell us about the remainder? When you're doing an oblique asymptote, you get to completely ignore your remainder and just use these numbers to get the equation. So since we started out with an x squared and we divided by x to the first, that means that we're starting out with x to the first here. So our oblique asymptote will be the line y equals 1x plus 2. Okay. Again, I'm not going to graph this entire thing, but I am going to show you how the oblique asymptotes can be used to help us. So let's at least look at what happens there. So for our vertical asymptote, we've got x equal 2. So we go to 2, we draw our dotted vertical line. This is a boundary for our graph. It's doing one thing here and one thing here. Our oblique asymptote is the line y equal x plus 2. How do we graph that? What's the easiest way to do it? Hopefully you remember from Algebra 1, this means that your y-intercept is 2 and your slope is 1. So find your y-intercept at 2. If my slope is 1, I can go up 1 and over 1. And then I can also go down 1 and left 1 to get 2 more points. Connect that with a dotted line. This is my oblique asymptote. So I've got 2 boundaries for this thing. It might be doing something inside here and maybe something inside here. Or sometimes it might be doing something over here and something over here. And if we were to graph this, which I'm not doing now, but if we were going to graph it, we would next look for our x and y intercepts to help us figure out if the activity is happening here or here or here. And then the intercepts are going to be very useful after we get our asymptotes. But that's how we find our asymptotes. And that is example 1. And we can go on to example 2. We have steps for graphing rational functions. So what does this say? Step 1, find any vertical asymptotes. Step 2, find any horizontal or oblique asymptotes. Remember, if you have one, you don't have the other. Step 3, find the y-intercept, if any. Step 4, find any x-intercepts that you may have. Step 5, determine whether the graph intersects its non-vertical asymptote by setting the rational function equal to the non-vertical asymptote. Okay, also notice that over here it says not common. Step 5, we're probably not going to encounter, so we're not going to worry too much about step 5, and we're going to look at step 6. Plot selected points in each domain interval which are determined by vertical asymptotes and x-intercepts, and then complete the sketch. Long story short, do your asymptotes first, and then look at your intercepts. A lot of the problems that you're doing in my math lab are going to be multiple choice. They're going to say sketch the graph, and then they'll give you 4 choices to choose from. Most of those, you should be able to determine the correct answer just by looking at the asymptotes and the x and y intercepts. That should give you enough information to find the correct graph. We're going to practice actually drawing some of these graphs when we practice these in class. So example 2, we're going to graph the function f of x equal 4x minus 2 over x plus 1. Alright, step 1 tells me to find my vertical asymptote first. Do I have a vertical asymptote? I set my denominator equal to 0. Solve for x, I get x equals -1. So that's my vertical asymptote. Do I have a horizontal or do I have an oblique asymptote? My numerator has degree 1, my denominator has degree 1. So they both have the same degree. This is when you just take the coefficients of the 2 leading terms. So we have a horizontal asymptote of y equals, we're going to just use the 4 and the 1, the coefficients in front of the x, 4 divided by 1, or 4. So I have my horizontal asymptote is y equal 4. Do I have an oblique asymptote? No, because I had a horizontal asymptote. So those are my asymptotes. Now let's determine our intercepts. Let's look for x-intercepts. You find x-intercepts the same way that we've done all the previous problems in the past. Let y equal 0. So you're going to have 0 equals 4x minus 2 over x plus 1. You can divide both sides, you can multiply both sides by the x plus 1, so that's going to give you 0 equals 4x minus 2. And then solve for x, so you get 2 equal 4x. Divide by 4, you get 1/2 equals x. So your x-intercept is x equal 1/2, or the ordered pair, 1/2 comma 0. And we just found one x-intercept. do we have Y-intercepts? Okay, we need to let x equal 0. We'll have y equals 4 times 0 minus 2 over 0 plus 1. So negative 2 over 1. So we've got a y-intercept, and I'm off the screen. Oh, I'm sorry. I didn't realize I was so far off. We've got a y-intercept of negative 2. So that will be the ordered pair, 0, comma, negative 2. We're going to have to go to a separate page to graph this. So I apologize. You might want to slip this extra page in your notes before you staple it all together. So just summarizing what we have. Our function was f of x equals 4x minus 2 over x plus 1. We found a vertical asymptote of x equal negative 1. We found a horizontal asymptote of y equal 4. We found an x-intercept at 1/2 0. We found a y-intercept at 0, negative 2. Now, with this information, let's see what we can do with our graph. So I'm going to draw a picture here. Make it kind of big because I'd like to have plenty of space to work with. Alright, so my vertical asymptote is at x equal negative 1. I can put a dotted vertical line at x equal negative 1. My horizontal asymptote is at y equal 4. So there's 4. Draw my horizontal line through here. I have an x-intercept. So notice again what's happened here. We can see this has divided the graph into 4 sections. We might have activity here and here. We might have activity here and here. All right. Since it's a function, if you've got something going on in here, you can expect this part to be blank. Same thing over here. If you've got something going on here, you can expect this piece to be blank because it's got to pass the vertical line test. So we've either got a picture here and here, or we've got a picture here and here. The intercepts are going to help us narrow this down. We found our x-intercept to be at 1/2 0, so we can go ahead and put this point in. This tells me a lot. Just this x-intercept tells me that I've got something going on in this part of the graph, which tells me that I don't have anything going on up here. So that's going to be very useful. My y-intercept was at 0, negative 2. Where is that? That would be here. So I'm still in the same portion of the graph. So it's not, you could think of it as the same quadrant of the graph. All right, but we need a little bit more information. So we're going to do a t-table to get a little bit more. So I see what's happening when x equals 1/2. Maybe I'd like to see what's happening when x equals 3. So if I put in 3 for x, where's my y? So let's do that one. Then I need to see what's happening on back here. I don't know if I'm working down here in this part or if I'm going to be working up here. It's going to be one or the other though. So let's choose an x value to the left of our vertical asymptote. So that's at negative 1. Let's do negative 2. Let's do, I'm going to do negative 1.5 because I want to see what's happening kind of close to my vertical asymptote. So I'm going to do negative 1.5. And then I'm going to do maybe negative 3. Let's see what's going on. Alright, so if I put in 3 for x, going back up, here's my function. If I put in 3 for x, what does that give me? That's going to give me 12 minus 2 over 4. So 10/4. Is that right? 4 times 3 is 12, minus 2 is 10. And 3 plus 1 is 4. 10/4, so that would be 2.5. So I've got 3 and 2.5 on my graph. Where's that going to put me? 1, 2, 3 on the x and go up 2.5 on the y. Okay, so I can get an idea for what this thing is doing just based on this much. Also, I don't remember if I told you, but if we go back to the first page of your notes, all right, I don't think I mentioned this, but this reciprocal function 1 over x, this was a very basic example of a rational function. All of our rational functions are going to be doing something similar to this. So you're going to have different portions of the graph, and you're going to have a smooth curve that's connecting the points. So it's going to look similar to this. So going back to what we have, if we connect the dots that we currently have with a smooth curve, and we also need to keep in mind that this is a horizontal asymptote, so that means the graph will never touch it. And we've got a vertical asymptote that the graph will never touch, but it will get pretty close to it, so it'll come back like this. And then you can connect these dots up here like this. So you need at least a couple of points from each section of your graph that you're trying to fill in. Now what about the negative 1.5? What's going on back here? If x equals negative 1.5, what is my y? I'm just going to substitute that back in. 4 times negative 1.5 minus 2 over negative 1.5 plus 1. That just came from substituting back into f of x. So what is 4 times negative 1.5? That would be negative 6 minus 2. Negative 1.5 plus 1 will be negative 0.5. So I've got negative 8 divided by negative 0.5. That's negative 8 times 2, so positive 16. Okay, so that is interesting. So we found that if x equals negative 1.5, which is 1.5 back, y is 16. So it's like off my chart. 2, 3, 4, 5, 6, 7, 8. So I've got to go like way up here off the camera to put my dot. What if x equals negative 3? If x equals negative 3, we're going to have 4. So we're going to have 4 times negative 3 minus 2 over negative 3 plus 1. That gives me negative 12 minus 2, negative 14. Negative 3 plus 1 is negative 2, so I get 7 this time. So when x equals negative 3, I got y equals 7. So where does that put us? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Now I've come down significantly to here. Okay, so that was where my first point was, way up here. In fact, it should have been, it's not very good. It should have been closer. It should have been more like, maybe like this. A little bit closer to the line. So we've got these 2 points. So I'm thinking it's going to do a curve, and it's going to be inside this section where it cannot touch. I know it can't come over here, and I know it can't come down here. So it looks like it's going to be doing like this. Let's put one more point in. We did negative 3, so let's put in negative 5. Where does that get us? Put negative 5 in for x and see what you get for your y. You should be getting 22 fourths. What is 20? That would be 11 halves. So that's 10 and a half. So when I put negative 5 for x, I'm getting 11 halves is not 10 and a half. 11 halves would be 5 and a half, 5.5. So negative 5 on x and 5.5 on y. And I can see it's getting closer down here. It's getting closer and closer to that asymptote, that horizontal asymptote. So I can draw my graph like this. So that's what my graph looks like. Again, it's very similar to our reciprocal function that we saw on the first page. Remember? This was the reciprocal function. It's just been shifted around. It's up here now. And it might have different pieces of the graph. It's similar to this. Basically, it's this graph that has been rotated and shifted around, and what we have is this graph here. All Alright, so I'm not going to ask you to do anything on a test much more complicated than what we've done here for graphing these types of problems. However, in the homework you're going to be doing some that are more complex. So you're going to have to be, like I said in my math lab homework, you should be able to find the correct graph if you just concentrate on the asymptotes and the intercepts. That should give you enough to narrow it down. We will be practicing these in class together, so we'll be getting plenty of practice with the graphing there. And again, your graphing calculator is there to use as a tool as well. Just make sure that you're not letting it do all of the work for you, but you can certainly use it as a reference. All right, now looking at example 3, we want to solve a rational inequality, and we're going to use the test point method for this. It's very similar to what we were doing with the quadratics in the previous sections and with the polynomial functions. We want to solve x plus 3 over x minus 2 less than or equal to 2. State the solution set using interval notation. So if you recall, when we were doing these with the polynomial functions, we had to first find all the roots or all the zeros. Very similar here, the zeros are going to come from the numerator, and then the denominator is going to give us vertical asymptotes. We have to use those as well because those vertical asymptotes, as we've seen, they divide our graph up into sections as well. And sometimes the graph might cross the x-axis at the asymptote. Before we can do anything though, we need to have our rational function compared to a 0 over here. We don't need to have a constant sitting over here. We need to be able to compare it to 0 because if you recall, the relationship to 0 tells us where our final answer should be on the graph. If you've got, you've seen this in previous sections, if you've got a big polynomial less than 0 and you're doing the test point method, the less than 0 method tells you that you want the sections that have the negatives for your answer. So we need to set this thing to 0 first. Let's subtract 2 on both sides. Okay. In order to find the zeros and the asymptotes that we need, we've got to put this together into a common fraction. How do we do that? Well, we need a common denominator. Right now this is over 1. We need to multiply the top and the bottom of this one by the x minus 2. So I've got x plus 3 over x minus 2 minus 2 over 1 times x minus 2 over x minus 2. They have the common denominator of x minus 2, so now they can be put together. Remember, when you're subtracting here. You are not multiplying. So you're going to keep the common denominator, the x minus 2. And in the numerator, you're just going to subtract straight across. Be careful about distributing that negative. That's where people usually get messed up. So all I did was I put the top all together into a single fraction, and I kept my x minus 2 in the denominator. Alright, then I can distribute in the top. I'll have x plus 3 minus 2x plus 4 all over x minus 2 less than or equal to 0. So I'm getting there. I've got to finish simplifying the numerator. X minus 2x, that's negative x. 3 plus 4 is 7. Okay, so now we've got it down to something that's not too bad to work with. Like we said earlier, the numerator is going to give us our zeros or our roots. The denominator is going to give us a vertical asymptote. Also, keep in mind you've got a domain issue. The domain here is all real numbers except x equal to 2. So if we are solving this thing, we have to remember that a 2 would not satisfy this inequality. So just kind of put that in the back of your mind for now. I'm going to put a note up here that my domain is going to be all real numbers except for x equal 2. X cannot equal 2, so that's very important. But now I'm ready to draw my graph. Oh, I didn't get my zeros, sorry. What root do I have, or what 0 do I have here? What value for x will make that numerator equal to 0? If I set negative x plus 7 equal to 0 and solve, I'm going to get x equals 7. So 7 needs to go on my number line. And then we also, in the denominator, we have 2 would make that denominator equal to 0. So 2 is also going to have to go on our number line. Even though 2 is not part of my domain, it is my vertical asymptote. So it will divide my graph into another section. So we're going to put these two numbers on here. We got the 2 and we got the 7. And then we're going to choose a number from each interval to substitute it back into the original problem, almost the original problem. Remember, your original problem was less than or equal to 2. That's you could use that, but I don't really want to. I think it'll be more straightforward if I use the version after I had simplified and got it to 0. So I'm going to be working with this. That's where I'm going to substitute my x values back into. Hopefully it makes sense why I'm choosing to put my values into this versus the original problem. You can put it into the original problem if you want to. Just be careful and remember that you're comparing it to 2 instead of 0. So I want to compare mine to 0, so I'm going to use this. So what do? Choose a number that's smaller than 2. So you can choose 0 back here. That's easy to work with. But if you put 0 into this problem, that gives you negative 0 plus 7 over 0 minus 2. So you have 0 over negative 2. I don't really care about the value. I do want to know about the sign. I got a negative, so that tells me that everything back here is going to take on negative values. It also tells me that the function is going to be below the x-axis. So I've got negatives all the way up to x equal 2. When x equals 2, what happens? Well, remember your domain? The domain said that x can never equal 2. So if x equals 2, that gives us an undefined value. I'm going to put a u for undefined because 2 is not in my domain. Choose a number between 2 and 7. So you might choose 3. Put 3 into your function. So I'm going to put it in here, and I'll have negative 3 plus 7 over 3 minus 2. That gives me 4 over 1. So is that positive or negative? That's a positive. So these are all positive. So now the graph is back up above the x-axis in this interval until I get to 7. What happens when x equals 7? If x equals 7, I put it here, and I've got negative 7 plus 7, which gives me 0. So that makes it 0 there. So this is like we did before, is 0. The only new part was that restriction on our domain that gave us the undefined value at x equal 2. In this interval, choose anything you want from this last interval. I'm going to choose 8, and I'm going to put 8 into my function for x. So that gives me negative 8 plus 7 over 8 minus 2. So that's negative 1 over 6. Again, I've got negative values, so these are all negatives. So that gives me my all my test points. Where is my answer going to fall? Well, it goes back to the relationship to 0. Our function needs to be less than or equal to 0, so it needs to be negative. So that means we choose the negative intervals. So we had all minuses here, so we're going to shade this part. And we're going to shade this part, where the minuses are. Hopefully it's clear to you that because the function is less than 0, we choose the sections that have all the minuses. Minus, 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 minus. That's our answer. How do we state this? Let's talk about the 2 and the 7 first. Is 2 part of our solution? No, because 2, remember, was not in the domain. I cannot put 2 into this thing because, I cannot put 2 into this because it'll give me an undefined value. So 2 itself is not part of my solution. How do I indicate that with a graph? Well, remember, you can use the round parentheses to show that 2 itself is not included, but everything up to 2 needs to be included. Is 7 included? Yes, it is. If you put 7 into this, you get equal to 0. And remember, they wanted to know when was it less than or equal to 0. So because of this little equals here, 7 is going to be included. So we could put a square bracket on 7. So this is a little bit different from the problems that we did before in the previous sections, because this time we've got a round parentheses here and a square bracket there, simply because 2 is not in our domain. So how do we give our answer? I'm about to run out of space here, but I'm going to put my answer down here. Okay, so I'm just going to take the shaded part of my graph and I'm going to express it using interval notation. So this piece I will read as negative infinity to 2. I'm going to use round parentheses. Because of this gap in my graph, or this open space, I'm going to use my union symbol. And then I'm going to start over here with 7, the square bracket, to positive infinity. So I got negative infinity to 2 with parentheses, union square bracket 7 to infinity. And that is example 3. That's as far as I'm going to go on these on the video lecture. I want to give you an opportunity to practice. And when you get in class next time, I'm going to give you some problems to practice first, and then probably the second hour I'm going to do those remaining examples, and then I'll let you work on some similar to that as well. So look forward to seeing you in class, and good luck with this stuff. And that's it. And this completes this section completes module 3. So the only thing left is just a couple of examples that we'll look at together in class with you. And bye-bye. Have a good day.